Hello, I am Amitov, and this is tinygrad verilog. My project where I implement a tinygrad backend in verilog. Here. Alright, let's get started. So, seems like 2 days ago now, but it's actually yesterday. Let me move this camera. I implemented like the layer, but I didn't test it because I was tired. So now is a good time to test it. So, let us navigate to layer.v. So our parameters, number of inputs and number of outputs, and then all of our inputs over here. So the nice thing about this is the way I've designed it is that we should be able to just like literally just chuck in all this stuff, like all the weights, biases, inputs at the start, and then just provide the clock signal. And the way this is designed, it'll like the module itself will iterate through the inputs, which is cool because then we don't have to do any like input or iteration stuff in the test bench. Let me move my camera out of the way. That is not my camera. There. Sure. Or, never mind. That's probably not important. Okay. Let us get started. So, test bench layer. Oh. I do not remember doing this. So, 4 of each seems like it'll be a pain. Let's just figure out right now what we expect the outputs to be. So never mind. That's odd. Okay, let me. So if we have 2 inputs, 2 inputs, 2 inputs, and 2 outputs, we can sort of represent this as 2 neurons with 2 inputs coming like that. And then each of them has their own output. So the way like our layer function module whatever is designed is that this is like all the neurons are encapsulated by the layer. ... And then when we're calling the module, we send in a bunch of inputs, and then the layer distributes them to like each of the inputs to each of the neurons. Here, and then each of the neurons has their own outputs, and these just get passed along. So now when we're building like the whole network, the way it'll work is that we'll have each of these will have like a stack of layers, but for now we can pretty much, here, let me, you guys, you cannot see my cursor. That doesn't matter. So let's just, if we have 2 inputs and 2 outputs, that means let's say our inputs are 1 and I don't know, 2. So let's define our weights. So weight 0, 0. So let's just say that's 0.5, 0.7, 0.3, 0.4. So I guess, wait, let me, I forget if it's, each row is, I think the way we have it is each row is the weights for a single input, not the weights for a single neuron. But that could be wrong. So generate what? Oh, git pull. Origin dev. Git stash. Git pull origin dev. Git stash drop. Okay. That makes a lot more sense. So now if we look at this, okay, this is clear now. The way we have it is we loop through each input, and then this is the weight for neuron 1. This is the weight for neuron 2, and then for the second input, this is the weight for neuron 1, and this is the weight for neuron 2. So if these are our weights and this is our input, then our outputs from each of the neurons will be here. 0.5 times 1 plus 0.3 times 2. Oh, and then, I don't know, let's just say our biases are 0.7 and 1.2. So then this plus 0.7, so this is y1, and y2 is 0.7 times 1 plus 0.4 times 2 plus 1.2. So the output we would expect is the output we would expect from each neuron is 0.5 plus 0.6 plus 0.7, which is, this is 1.1, so this is equal to 1.8, and then over here this is equal to 0.7 plus 0.8 plus 1.2. This right here is equal to 1.5. So this comes to, in total, 2.7. So our outputs are 1.8, 1.7. 1.8, 2.7. And yeah. So now to the way each of these are represented in our, so each of these are 16 bits. Now over here, it's coming from the right, it'd be 0.5, 0.7, 0.3, 0.4. Yes. Okay. So this is the order in which we have to allocate our weights. Both of these are already okay because they don't have multiple rows. Wait, sorry. All of these are, no, this should be inverted because I think it'll be clearer if I just actually do it. So let's see what we have here. This is just incorrect here, and then 16 times 2, so that's 31, 31, and then 4 times 16 is 63, and then the output's 31 bits, 32 bits. Here, cool. Note to myself. These are our helper functions from before, and then, okay. What the? That's odd. Oh, I probably implemented this before, so I don't understand the syntax. Open code. Hey Jarvis. Hey Jarvis. Ah, doesn't work. Well, here. How do the curly braces in tb layer.b on lines 40, 48 and 51 work? Explain the syntax. Okay, each of so the first element in the list becomes I haven't saved this, that's why. So that makes sense. That's the way I explained it before. We're just concatenating, and then over here, again, this is from before, and this format is outdated from what we're using now. So why am I here? Real to these are the inputs 1 weights. So real to Q8, what was it? 0.5, real to Q8 0.7, real to Q8 0.3, real to Q8 0.4. Is this correct? Looks correct. There. The indentation looks off. Here. There. Okay. Biases. Over here, our biases are 0.7, 1.2. Wait, oh wait, this is backwards. Here, so the way right. Yes, because it goes from right to left, but this is concatenating on the right side. So wait, the way I changed it is wrong. This was correct. Yes, and then over here this becomes 0.4, this becomes 0.3, this becomes 0.7, and this becomes 0.5. That looks correct. And then the biases are 1.2, 0.7. Yes, here, and then here. Okay, now see over here, set start to 1 and then set start to 0. That looks good. Then we wait 200 nanoseconds. That seems fine. Here, here. Okay. Let us run this test now. I have a feeling something's going to just sort of break, but we can fix it. Makefile. Test. Do I have test layer? I do not have test layer. Great. Here, test layer. layer.vvp source.v tv layer.v. Hopefully this should work. Now I can run make test layer source.v. Where did I source/layer. Increment decrement operator requires system verilog. Cool. Layer.v. (22). Can I just do I equals I plus 1? I can just do I equals I plus 1. Now I'm getting a bunch of go to line 51. Is that because of the comma? If I here, I think it was because of the comma. Now if I go to 64, and then 85. Syntax error. There it is. Also, where is the closing parentheses? Parenthesis. That makes sense because I just deleted a bunch of them. Line 80. Oh, right, because these are expecting 4, but I'm only providing 2. Oops, what the, nope. Here, syntax error still. 81, this is just incorrect. Why is the indentation weird here? That looks like something. Ooh, wrong key. Here, there's an extra comma here. Here, now if I, no. Huh. Make test layer. Syntax error. Line 81. Let me, wrong. Here, let me find test bench neuron. How does, like, what is this doing differently? hey, open code, why am I getting syntax errors near the display statements? Wait, what is this finishing? Odd. And at TV layer.v. Missing, that makes sense. Here. Semicolon. I have been spoiled by Python. Semicolon, semicolon. Now, save. Ooh, that is not great. Not support of UUT. Layer. Oh, is this supposed to be like key here? What? Xval is declared here as a wire. Neuron.v. Nope. $15 is not a port of UU. Oh, okay. I think the problem is I just have different port names over here. Yes, I do. This should be X, this should be W, this should be B, and that is already Y. Net activation is 32. Is not defined in this context. Yeah, that's odd. I'm guessing the reason we get it twice is because of the, oh, it's a wire. If I change this to a register, do we still get these messages? Yes, we do. Is not defined in this context. Output port expression, it's a wire over here, is it? If I change this to register, still port 6 activation of neuron is connected to activation SD16 times I minus is this because of the like weird stuff we're doing with I mean we're not getting the errors elsewhere. Valid L value. Open code, continue. Here. Okay. Here. Why are we getting these errors? Isn't like, yeah, isn't a register supported for continuous assignments? Attempts to connect to activations. Okay, yeah, it looks like Gemini is having some trouble. Let me model slash models GPT 5.1 codecs. Here, continue. Hopefully, yeah, I know I always have like troubles with Gemini sort of just not working with tool calls and stuff. Okay, it looks like, just from what I saw, it has to do with invalid indexing. Oh, I see it now. Here. Does it work now? Test layer. Never mind. Sorry, continue. That's odd. That was definitely part of the reason it wasn't working, because we would have been indexing from like bit 16 to bit 15, which does not make sense. let's look at the other errors while we're waiting. Xval is not a valid L value in is not a valid L value verilog. Trying to test if a wire is on or not. So output reg 3 sign error is not declare error and overflow. Oh, do these need to be are these wires? Yes, they are. That makes sense. If I change these to reg. Oh. Interesting. Changed done to yes. That is odd. And then changed activations to wire, and then xval and yval, and xvals and wvals to there. Okay, that holy. Oh, no. Never mind, that looked scary, but I think it was just I mean, it looks like it just changed the order of things. Yeah, right now I don't really understand I don't understand well enough the difference between registers and wires. They seem sort of like I don't know, arbitrary. Here. Ton. Odd. Who? A reference to it's not wire or reg. Add in a constant expression. Part select expressions must be constant. Well, if this were constant, that would break the logic, because then it would not I mean, it wouldn't work for iteration, and then that makes sense. We get the errors every time it iterates through. count. Let's see. Count is assign count to 0. 0. What is this? Okay. I mean, does not look constant. And oh, what is this? What is this for? Here. Okay, so it's running the test bench again. Okay, I'm just gonna interrupt it and run it myself. 30 neuron unit test. That's weird. Make file layer. Exit, quit, help. What the hell? PS aux grep test layer kill 2340. Okay, let's run that again. Inputs, outputs, that is not good. Why are we getting zeros? Well, I mean, it is good in a way that we didn't get any errors, but that does not make sense. Here. This is incorrect. Can we, like... Let's figure out if it's a problem with, just like the structure itself. So let's just change this to just one input, one output. How do I just quit? Right, that doesn't work. Kill 2340. 2340. 23111. We can deal with that later. Here. This, now all these will be 15. This will be 15. So really this is just adding multiplying, adding, and then ReLU. So if we go down to here, let's just two here, 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 ooh, oh, wait, these are incorrect. 15 to 0 and 15 to 0. Now if I clear make test underscore layer unit test, output 0. Okay, that is bad. Control Z. Let's figure this out. If we change this to 1 and this to 0, try again. Yikes. Okay, it looks like there is a problem with the layer itself. Okay, can you explain to me the difference between registers and wires and why in layer.b you used them where you did? Holds value between clock edges. That makes sense. Let's explain the 43 to 52 plus signs after before the colon and the slices in lines 43 to 52. Indexed part select. Okay, it's odd that we are getting zeros I don't think it's a problem with the neuron. Make test neuron. So that's not the problem. Okay. So it's a problem with, are we feeding them the values correctly? If we I don't know, if we just like copy this layer dummy.b and here paste this, and then I wonder like if it's actually okay. We're getting zeros. Well, I'm getting zeros when running the test bench. Are we sure that the neurons are receiving their regardless of inputs, receiving their weights, biases, and inputs? See if you believe it. Okay, while we're waiting for this, once we do get the layer working, guess then the network should be easy because you just like chuck in a bunch of numbers and then you like wire together a bunch of layers and then you wait for it to vomit out an output, and after that we'll be done the forward pass. Then we'll have to do the backward pass, for which I have no idea how it'll work because yeah, je ne sais pas. So I guess like, yeah, this is it like actually doing stuff? What the hell? This is different. Here. Exit. It looks like it's frozen. Claude Opus 4.5. Code continue. Hey Jarvis. Hey Jarvis. Not working for some reason. Sorry. Continue. Must. Hello? What the hell? All messages must have non-empty content. Okay, let me just make a new session. Why am I getting an output of 0 when running tb layer.b? Continue. So, here, don't you see the outputs? Why are you running it again? What? At clock edge, delay this is nonsensical. We already initialize values in the test bench before starting, before setting start to 1. Here. Start reg start delayed. Start delayed is start and wait. That is are you reading at layer.v? We instantiate the neurons before the procedural block. On the same clock edge, sure. Okay. Start delayed. Still 0. Y is done 0 in the layer unit test. That's weird. Done, and the output still 0. What the hell? Okay, new file. Y is showing X. One more. Here, okay, so start delay 2, start, what the? That's odd. The neon works. Ready on the pause. We need here. Okay, so we've removed okay. Amazing. Okay. Now it's working. If I reload this, let's walk through this and understand what's actually happening. So now we have two more registers, start delayed and start delayed 2. And then over here, okay, so the indentation's weird. Here. So start is connected to, so each of the neurons starts on start delayed, and start delayed is equal to start, and start delayed 2 is equal to start delayed. So if start begin count equals 0, xval, so we load the first input and the first wait. Then because of this else if, then start delayed comes after. Okay, amazing. Where is start delayed 2 used though? Can we remove it? Okay, so now let's let's go back to our earlier test bench. Okay, so now clear make test layer. Outputs 1.699, 2.598. Those look like just precision errors, I assume. Yeah. Okay, amazing. Our layer is working. Okay. Now, let's get started on the network. Here. So, let's figure out let's keep it simple and for now just have, I don't know, a 2 there. So inputs, we start with 2 inputs that come in here and then go through here to the next layer and then finally come out. I don't know. Let's do XOR. What the? So that's XOR is our first problem we'll be optimizing for. Then when designing the network, for now I think it's simplest if we just enforce that all layers must have the same number of neurons, because then we can just have a parameter like number of yeah, just number of neurons per layer and number of layers just in total, and then we just have the number of inputs and the number of outputs be what? We have the number of inputs be equal to the number of outputs. Yeah. I mean, later we can figure out, I don't know, if I want a network that's like this. I mean, like, the actual implementation shouldn't be too much different, because really you're just hooking up a bunch of like already existing layers together, but I'm not sure like how you would specify something like this, right? We can figure that out later. Let's get to work, I suppose. So, number of neurons, number of layers. So, the number of inputs should be equal to, well, the number of neurons, inputs, outputs. So, inputs, their weights, that's what? Oh, this is just a layer module. Okay, so for something like this, we'll need number of inputs times number of neuron weights times number of layers. And because number of inputs and number of neurons are the same, this is just equal to n squared times m times 16 bits. Yeah. So for this with n equals 2 and m equals 2, this would be equal to 4 times 2 times, so 4 times 2, which is, so that means 8 weights, and just like W00, W01, W10, W11, W2, 4, W2, wait, 0, 1, 2, 3, 4, W2, 5, W3, 4, W3, 5. If we count these up, that's 1, 2, 3, 4, 5, 6, 7, 8. 8 weights. Amazing. Okay. So number of inputs, this is correct, and then W times n times 16 minus 1, 0. Okay, and then biases, that would be number of neurons times number of neurons times number of layers, and then number of outputs will just be number of neurons. Yeah. Okay. Okay, that works great. Explain to me again the difference between between wires and registers, and when to use each. So this will just be so the way, I guess for this we'll need to have intermediate states, because the thing is we can't just hook up we can't just sort of instantiate each of the layers and hook them all up to the outputs, because you can see here this layer's outputs are not going to the output, this layer's outputs are going to the next layer. So I suppose that would be m minus the size of the intermediate states would be the number of layers minus 1, because minus the last layer, and then times the number of outputs per layer times 16 bits. M minus 1 times n times 16. Okay, so intermediate states. Can we have if statements in not? I feel like we have something like that in non-procedural genbar blocks. No, you cannot. Here, can we modify the parameters of a generated block of a generated, I guess, instantiated generated module? Specifically, right now I'm implementing the full network structure, which is just a bunch of layers glued together, and I want to hook up the outputs of each layer to the input to a slice of an array number. Here, let me move this so you can see what I'm typing. To an of an array like number, like how we for weights and biases and inputs and such in the layer module, except which contains intermediate states, except for the last layer when I is equal to m minus 1, where m is equal to number of layers for which I want to hook up the output to directly to the output. That makes more sense. Okay. So Claude had a good idea there. We can just remove this m-1 business and just make the entire thing the intermediate states. We store everything in store everything in intermediate states, and then we can just assign the output to the last slice of intermediate states. So let's see. Reg C log 2 m plus 1 minus 1 0 count. What the hell? That is really odd. Here. There. Here. Okay. I suppose we'll need to have register signs. So it doesn't need to be a register, cause it shouldn't be. Oh yeah, it does need to be a register because it's updated. We're going to update this every time we move to the next layer. So here, let's go up. Okay, so for this it'll be m times n times 16 minus 1 to 0. This should be there. Okay, and then I think that's it. Do we need the start delayed in this as well? So over here in the layer module, we use start delayed because actually, why did we use start delayed? Can you explain bins and why we had to use start delayed? I'm contemplating whether or not to use something similar in the network module. Here on this okay. So it's because it's non-blocking. So how will we, the way I think it would make most sense to iterate through is to, at instantiation time, no. Yes? Why did we, what are we actually loading over here? Because they're looping, okay, because we have an array of all of the inputs, well, wait, why couldn't we just assign each generated module a slice of the input wait, no, okay, it's because every module, every neuron needed every inputs. That's true. Yeah, so if we had just, it wouldn't have made sense to assign. Fuck. Sorry, I just started playing music. It's still playing music. And now my headphones is connected. And I can't find my headphone case. Gee. Wait, is this? Oh, I suppose my headphones haven't been connected to the computer. They were connected to my phone. I hope you guys can hear me. On OBS, it looks like you can hear me. Okay, that makes more sense. Well, right, we were talking about instantiation stuff. So I don't think we need to load the values when it comes to the network, because unlike the individual layers, unlike the neurons in each layer, not every layer needs the same inputs. So we might not need to delay the start to wait for everything to be loaded. Yeah, and then we can just, I think it makes most sense to structure our weights by layer. So we just have starting, so I guess layer 0, weight 0, 0, then layer 0, weight 0, 1, layer 0, weight, this is layer 0, weight 0, 1, then layer 0, weight 0, n, and then layer 1, weight 0, 0. So then we can just split this up by this would be the first n, so first n squared numbers, because the number of inputs are the same as number of outputs. The first n by the first n times the first n squared numbers belong to the first layer, and then the next n squared numbers belong to the next layer, and so on and so forth. So we can just, because we're fed in all of the weights at the initialization of the network, we can just assign each of the layers a static number of weights. That might not work too well when we're expanding it to include a backward pass, but I think we can figure it out then. So yeah, we do not need that variable either. So gen var I assign y equals intermediate states. That'd be m times n times 16. Here minus 1 to m minus 1 times n times 16. There. No matching. That's odd. Okay. Generates for I equals 0. I is less than m. I is equal to I plus 1. Begin layer, then the parameters n m n here neuron inst dot clk dot start dot x okay, I think we'll need, if we want to keep this clean, we'll need to make this m plus 1 and then assign the first m times n times 16 bits to x. So that way we don't have to, like, if it's the first one, make the inputs x, otherwise make the inputs intermediate states. That seems like it'll overcomplicate things. Here, m plus 1, and then m, what was it? Like, they had some special way of, here, how is the, what is the plus 4? Did I miss it? Here. assign intermediate states, so that it'd be n times 16 minus 1 to 0. The first n numbers equals x. Feel like I have a feeling that's gonna be wrong somehow, but alas. Okay, so let's go up. So equals intermediate states, so that'd be I times n, or no, I plus 1 times n times 16 minus 1 to I times 16. No, I times n times 16. Here, and then what inputs does this thing take? W, so that'd be W, so to I plus 1 times n times 16 minus 1 to I times n times 16, mismatch parentheses here, and here, and if we go back down, wait, okay, so then biases, that'd be I, or maybe, so B, I plus 1 times n times 16 minus 1 I times n times 16. What? Okay. Here, and then the outputs shall go to intermediate states, so I plus 1, or I think it'd be I plus 2, because we're already assigning the first n times 16 bits to the input passed in. So that'd be I plus 2 times n, another parenthesis, times 16 minus 1 I plus 1 times n times 16. Then close that, and then what could be interesting is like have n bit have shut up, sorry, alarms. I guess would that be like I suppose like wire m minus 1 to 0 intermediates done, or probably just 1 second, I'm gonna go to the bathroom. Hello, I have returned. Intermediate's done. So we'd want to have one for every one for every layer, and then we can just assign done equals intermediate done. That'd be m to m minus 1. That's 1 bit, right? I sure hope so. Wait, or just m to n. I am not sure. There. Okay. And done. Intermediates done. I. Then close this and generate. What? Okay. There. So now the procedural block. Start. Okay. think we'll also want intermediate start. X here, forgot semicolon, wire m to 0, intermediate start, then can that here. So we want to assign intermediate start uh, 0 is equal to start, and then yeah, because oh, but then we might get some issues with like race conditions, because when does this actually trigger done? So like if we just naively assign start to done, what could happen, which is bad, is that basically we could start the next layer before the previous layer has finished processing. Okay, OBS just stopped recording for some reason. Something about like an encoder taking too long. So if you're watching this, I'll probably have used like KDEN live or something to like splice the previous clip onto this one. If you're hearing this, I probably didn't take that much time to do it because I couldn't be bothered making it good. But anyways, you should have the full context. Sorry, I'm like really... Right, what we were doing before that was figuring out how we were going to trigger every layer to start. So the problem, like the naive way, is just, you know, assign like basically assign intermediate start I is equal to intermediate done I minus 1. So this is the first thing that came to my mind, and like it makes sense when you first think about it, because you know, like if I finish the previous layer, well then I'm ready to start the next one. But the problem right now is like basically over here these like these are non-blocking assignments, which means that xval and wval is getting assigned at the same time as done. And what that means is that if we just naively assign the start of the next layer to the done of the previous layer, what will happen is that that clock edge will come, and then we'll check and see, oh, count count plus 1 is equal to n minus 1. We're done. So then we'll assign that, but the problem is we probably haven't yet assigned our x and weight values, and what that means is we probably haven't computed the final output. So what that means is if we start off the next layer, it's probably working off of not the final state, but the state of, well, actually it would probably just be 0, I think. I don't fully remember how the neuron works, if it also assigns, actually we can figure this out here. So dot here, activation. So yeah, looking at this, what would actually happen is we wouldn't have finished the multiply accumulate, so our activation would just be 0. So if we did that, everything would just be 0. So yeah, that's bad. Here, Claude. Okay, I have a conundrum. What? Here. Okay, we've saved this. I'm trying to figure out how to trigger each layer in network V to begin when the previous one has finished. The naive solution I was initially considering was something like assign intermediate start I equals intermediate done I minus 1. Something like passing in intermediate done I minus 1 into the start input of the ith layer module, but I believe I before E except after C believe that would create a race condition, because in layer.v layer at layer.v we assign done to done to 1 when count plus 1 is equal to n minus 1, but that happens at the same time as we assign the last X val and W vals, which means that the Mac wouldn't have finished, and so the output of the layer would not yet be present, so we would get all zeros. What's the best way to avoid this? That makes sense. Yeah, that seems like a reasonable solution. So yeah. Is there a chance of a single neuron finishing before the others? There a way we could here have done be neurons done be a not array wire of m bits, then have done only trigger if neurons done is all one. Here. Okay, so wire m-1 to 0, neurons done. So then let's assign this to neurons done I, and then assign done equals and neurons done. So let's one errors okay, I assume the fix there is to just change this to a wire. That sucks. TV layer done. Dun 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 dun. Do we reference? Oh, that's it. Okay, that we can just remove this. Like, I think we can just remove all these because done is now being driven by continuous assignments. Here, layer fee 11. Done is not a valid L value. That's odd. Line 55. Done. Oh. I assume we can just do that. Yep. Cool. So now that we can be sure that we won't get any race conditions, now we can I guess we'll have to make intermediate done would be m-1 bits because no, m bits and then can we like assign intermediate start m to 1 is equal to intermediates done like that? So from there, start is equal to intermediate start I or I-1. I'm worried I'm gonna get like off by 1 error somewhere. So for the first layer, okay, I think we should be good. And then after ends generate comes the always block. Pause edge, CLK, begin. So we already have start and done assigned. We already have start assigned. So it will start as soon as the test bench tells it to. So what here is procedural? What do we need to put in the procedural block for network? The given that the start and done and weights and spices and inputs are all driven by continuous side. Holy smokes. Holy smoke. Holy smokes. By and outputs assignment. Assume that we still need a procedural block. Do we actually though? Given we're just connecting the inputs clock to the network directly to the inputs clock of the layers. Line 24. Indeed I am. Here, okay, okay, does network.v look good now? I've assigned intermediate start 0 to start and done to intermediate done. Suppose the intermediates in those variables would now no longer be strictly true, but who really cares? Off by 1. Why isn't it like writing to the file? Oh, yeah. Off by 1 errors. Here. So this should be m minus 1. because one for every layer, and this would also be m-1 because it's one for every layer. So intermediate start 0, and this is equal to states m-1 to 1 is equal to m-2 to 0, and that. Okay, let's make a test bench for this. TV network .v. This looks good to me. TV layer. Okay. Module. Oh, did I end the module? Yes, I did. Here. Module TV network. Register clock. Register start. Reg signed. So if we're doing 2x2 network, that would be how many inputs? 2 inputs. 31 to 0 spells. Register signed. So 8 weights. So 8 times 16 is 8 times 8 times 2, 64. 127 to 0. That is how many bits? And then 4 times 2 times one bias for each layer. Wait, I forget. It one bias. Is it one bias per layer or per neuron? One bias per neuron. So 4 times, that would be 63 to 0. B vals, and then wire assigned the output of 2 neurons, 31 0 y vals, and then of course wire done. So network hashtag, so number of neurons to number of layers 2 as well. Here, unit under test. Okay, now let's open this back up. So dot clk dot start dot x vals dot y w vals. Here, let's yep, by dot b vals, and then dot y dot done here. Okay, think that's good. Now let's go back over here. Let's copy this boilerplate over. here, initial begin, display network units test. So let's figure out what we want our inputs to be, and weights and whatnot. So I think, like, keep it simple. X equals 1, 2. So, well, that'd be, in our format, that'd be concatenation 1, nope, concatenation 2, 1, obviously wrapped in real to Q8. I don't know if that was obvious. And then our weights would be, just make these up, 0.2, 0.5, 0.3, 0.4, 0.8, 0.1. How many is this? That's 6, 2, 3, 4, 5, 6. 0.7, 0.9. Okay, and then biases, that is 1, 0.5, 1.2, 0.6. Okay, let's figure out what our expected output is. So here, 1, 2, that's 0.9. So the output of this neuron is 1 times 0.9 plus, skip there, 0.1 times 2 plus 0.6, so that is equal to 0.9, 0.2, so 1.1, 1.7. 1.7. 1.7, and then the output of the second neuron is 1 times 0.7 plus 2 times 0.8 plus 1.2. So 0.7 plus 1.6 is 2.3, so that's 3.5 for this output. 1.7, 3.5, and then the output of this neuron would be, I'm just gonna do it over here for sake of convenience. So that'd be 1.7 times 0.4 plus 0.5 times 3.5 plus 0.5. So that's equal to, I'm just going to use Python 1. x equals 1.7 times 0.4, y equals 3.5 times 0.5, print x, y. 0.68, 1.75. So 0.68 z equals x plus y plus 0.5. Print z. 2.93. 2.93. And then for our final neuron, 1.7 times 0.3 plus 0.2 times 3.5 plus 1 here. So x equals 1.7 times 0.3, y equals 3.5 times 0.2, z equals x plus y plus 1, print z. 2.21. 2.21. So these right here are our expected outputs. So here, close that, and here x vals equals real to q8 2.0 comma real to q8 1.0 brace semicolon w vals equals real to q8 0.2 comma real to q8 0.5 comma real to q8 0.3 comma real to q8 0.4 comma and then real to q8 0.8 comma real to q8 0.1 comma real to q8 0.7 real to q8 0.9. So then we can brace here. Finally, revals equals real to q8 1 real to q8 0.5 real to q8 1.2 real to q8 0.6 there and CLK equals 0 start equals 0 here. So now we wait 20 nanoseconds. Oh, didn't do the declaration at the start, but looks like it doesn't matter because we did not get any errors last time. Start equals 1. Do we have to set start to 0? I don't suppose so. let's just wait for, I don't know, that much time. And then here, here. And end module. Here, here, save, and then here, let's make sure everything is in our, oh, it just includes all. Amazing. Test network. Port 6. Oh, that doesn't look good. Expected 32 bits. 1. Cannot select part of scalar. That's network. What? Here. To bind. AT1. Oh, that's because this does not exist. Shit. That sucks. Network. Here. Okay, make test layer. Okay, so the layer is working, but the network is not. Okay, for some reason, in at TV network, nope, at TV network, we're getting zeros. Pourquoi? Ah. Here. 2.918 and 2.195. Those look correct within floating points error. Okay. That is a forward pass. Amazing. I have to get ready for school now. Next time we shall figure out the backward pass. Goodbye.